Whew, this one looks a little interesting. Using the results from the previous two problems for DHDP and DSDP, calculate delta H and delta S for the isothermal pressure increase of CO2 as a van der Waals gas from 1 megapascal to 15 megapascal at 298 Kelvin. These are the values for the van der Waals constants for CO2. And then they ask us to run the same calculation at 598. And then they say, compare the values you calculated for 298 to those obtained for an ideal gas. Okay, so we just found expressions for a van der Waals gas for the change in enthalpy with respect to pressure, the change in entropy with respect to pressure. We can integrate these expressions to get expressions for the actual change in enthalpy and the change in entropy. And then we're going to compare them to the van der Waals, compare them to the ideal gas. Okay. All right, so let's see what we've got. So we want to know what delta H is, and we want to know what delta S is. And let's see here. So let's go ahead and write down, let me see, delta S. Okay, so from our free, let's actually write down what we've got. So our CO2 gas, we're taking it from 1 megapascal, we're taking it to 15 megapascals, and we have our value of, well, that's fine, we'll go ahead and put those in a minute. So A equals 0.366 meter 6 pascal per mole squared, and B is equal to 42.9 times 10 to the negative 6 cubic meters per mole. Okay, so from the previous example, we found that dH dP at constant T is equal to B minus 2A over RT. Therefore, I've got dH equals B minus 2A over RT dP. And then when I go ahead and integrate this expression, I'm going to get delta H is equal to B minus 2A over RT times the integral from P1 to P2 of dP, and that's going to equal B minus 2A over RT times our delta P. Okay, so our delta H is going to equal, and again, this is molar, so it's, well, that's fine, doesn't matter. So we've got B minus 2A. So let's just plug in all of our values. So we have B, which is going to be, we have 42.9 times 10 to the negative 6 minus 2 times 0.366 all over 8.314 times 298 times delta P. So it's going to be 15 minus 1, and I'm going to do times 10 to the 6 because this is megapascal. So we're working in pascals. We're working in pascals in order to make sure that the units match. So 15 minus 1 is 14 megapascal. It's 14 times 10 to the 6th pascal. When I do this, I get a delta H of minus 3,536 joules per mole. That's all this line means, molar. There we go. That's the delta H based on what we calculated for DHDP and then integrated it. Okay. Now for the DS. Well, we worked out that DSDP under constant T, that's equal to minus R over P plus RA over RT squared. Therefore, our DS is equal to, when I move the P over, I integrate the expression, I'm going to get from P1 to P2 of this thing, R over P plus RA over RT squared dP. Okay. So ds equals minus r times the integral from P1 to P2 of dP over P. This minus comes out, so this becomes a minus, and this becomes a minus. It distributes over both. Minus A over RT squared, I canceled one of the r's, times the integral P1 to P2 dP. Therefore, our ds is equal to minus r ln P2 over P1 minus A over RT squared times delta P. Okay, now we put the values in. Delta S equals minus 8.314 times the natural logarithm of 15 over 1. The megapascal cancels megapascal, so I don't have to go ahead. If the units cancel, I can leave the numbers alone. Minus 0.366 over 8.314 times 298 squared times 15 minus 1. And again, this one times 10 to the 6th, because there's no cancellation here. That equals, I'm going to do these separately, minus 22.5 minus a 6.9. Therefore, the entropy change is minus 29.4 joules per Kelvin mole. There we go. That takes care of the delta S. Okay, so let's see what's next. They asked us to run these same calculations, part B, under a new temperature. Well, it's the same exact process, same exact thing we just did. The only difference is instead of 298 for the T, we're going to put 598 for the T. So what we end up with are delta H. I'll go ahead and put 598. It's going to equal minus 1460 joules per mole. Okay, and the delta S is going to equal minus delta S at 598 is going to equal negative 24.22. Yes, negative 24.22 joules per mole Kelvin, or Kelvin mole. There we go. Okay, now let's go ahead and compare the two values. Well, let's see. C, they wanted us to compare the values for the ideal gas and the van der Waals gas. Okay. The delta S for the ideal gas, that's equal to minus R ln P2 over P1. That was the first term. Well, I'll get to it in just a second. It's minus 22.5 joules per Kelvin mole. Delta H for the ideal gas, that equals 0. And the reason it equals 0, because dH over dP T equals 0 for an ideal gas. Remember Joule-Thomson coefficient for an ideal gas. And I'll put Joule-Thomson. Now, in case you're wondering where this came from right here for the ideal gas, just look back on lesson 21. Lesson 21, which is the entropy changes for an ideal gas. Entropy changes for an ideal gas. Now notice this expression right here. This was the first half of the expression for the van der Waals equation that we just did in part A. So the van der Waals expression, remember I did it in two, minus 22.5 minus another value. So that minus 22.5, that takes care of the ideal gas portion of the van der Waals gas. And then because it's a van der Waals gas, there is actually an additional term. It's no different than the van der Waals equation. So remember, we had a negative 22.5. So that's it. Thank you so much for joining us here at Educator.com. We'll see you next time.